Hello and welcome everyone in today's webinar on unconventional multi-well history match and optimization, a Bakken case study. My name is Anjani Kumar and I'm the Vice President of Engineering Solutions at CMG. I'll be the moderator for today's session. We are all working through and adapting to new concepts like social distancing, self-isolation, working from home, and flattening the curve, all part of our cooperative effort to slow and hopefully limit the spread of COVID-19. While the limit of uncertainty can be unsettling, the most important thing we can do right now is to focus on the things we can control. With that in mind, first and foremost, please take good care of yourself, physically and mentally, and stay safe. In today's webinar, I'd like to introduce Kevin Jocelyn, Senior Reservoir Simulation Engineer at CMG, who will be presenting today's webinar. Kevin has over 7 years of experience in modeling of unconventional fractured oil and gas reservoirs. Kevin has conducted several reservoir engineering studies for optimization of recovery, either from primary or enhanced recovery processes like miscible huff and puff or gas injection. For the past several years, he has also been involved in modeling of geomechanics-based hydraulic fracturing and investigating the impact of frac hit on production from parent and child well interactions. Kevin holds a bachelor's degree in chemical engineering from University of Calgary. At this time, I'll also like to inform you that there will be a question and answer at the end of the presentation. However, you may submit your question at any time using the chat window on your screen. We will also post the recorded version of the presentation within the next 24 hours on our website. You can use your CMGL login and a password to access the material. Also, there are several online training courses that are being available to register and attend. So watch out for our posts on LinkedIn, on our website, and through other social media platforms. So over to you, Kevin.
Thank you, Anjani. So as Anjani mentioned, today's presentation is an unconventional multi-well history match and optimization focused on a Bakken case study. And I'd just like to mention that this case study was performed for Continental Resources. So I'd like to thank them for giving us permission to present this work today. So before we get into the content, I just want to talk about the agenda of what we're going to talk about today. So we'll start off with just a brief introduction, just kind of set up the problem statement, what questions we're trying to answer. I'll then go into the simulation model construction. I want to talk about some of the key points that we came across from this project in just constructing the initial simulation model. We'll then talk about the history match that was performed, and then that'll lead into the optimization. In the optimization, it is a well spacing or well density optimization as the primary focus. And then lastly, we'll wrap it up with a few conclusions. So the image on the screen is a map of the United States with some of the key unconventional or tight formations across the country. Each of these different formations has their own unique set of sort of challenges and properties, but the workflow that I present today should still be applicable to each of these formations. Today, we're going to be looking at the Bakken, which is located in parts of North Dakota and Montana, as well as parts of Saskatchewan in Canada. Some of the characteristics related to the Bakken is that it's mostly composed of volatile oil and black oil, and the permeability within the Bakken tends to range between 0.1 millidarcy down to 0.1 microdarcies. So something that's sort of been a characteristic of the Bakken, as well as many other unconventional assets, is the amount of wells that are currently being drilled are all infill wells. So an infill well is when we're drilling close to an existing well as opposed to drilling into virgin reservoir. And really coming up with the appropriate placement of these infill wells, or sometimes called child wells, is going to be the key for the continuing development of these assets and formations in the coming years. So let's take a look at the development area that, or this particular project. So in this project, we first are going to perform a history match of 10 wells. And those 10 wells are sort of broken up into 2 development areas. So we have development area 1, which consists of 5 parent wells. And then we have development area 2, which has a single parent well and then 4 child wells. So 10 wells are already drilled. Then that'll lead us into our optimization, where we're going to do a well spacing or well density optimization for development area 1. So basically the area where we only have parent wells currently. If talking about the Bakken here, the Bakken itself is composed of three main layers. So we have the upper Bakken shale, the middle Bakken, and then the lower Bakken shale. Within the middle Bakken, although it's not a shale rock, it's still considered a tight reservoir as the permeability is quite low, as mentioned previously. Below the Bakken is another formation called the Three Forks Formation. Within the Three Forks, this is composed of some internal shale layers, as well as some pay target zones as well. Okay, so let's get into the model building. So the first question that we have to ask ourselves is how we're going to orient our grid. And we really have two choices. We could choose the option on the left, where we orient our grid in the direction that the fractures are growing. So the fractures will tend to grow in the direction of maximum stress, as shown in the image on the left. Or we could orient our grid with the image on the right, where the fractures are growing perpendicular to the well. Both are certainly acceptable, but we need to think ahead, think long-term to when we get to our optimization stage. When we get to the optimization stage, we're going to be looking at a lot of different well spacing scenarios and moving our wells to different locations. So to make things simpler and easier on ourselves, the option on the right is more desirable. However, if we do decide to go forward with the perpendicular grid, we need to make sure that we are calculating the correct, basically effective half length. So to do that, we can take the true half length if our fracture is oriented such that it's not perpendicular to the well, and then calculate an effective half length so that we're still honoring the correct, basically SRV or stimulated reservoir volume. Just to make sure that both of those cases do produce the same results, we can run them together, run those two simulations. In the screen here, we have the BHP for one of the wells, and we can see that it's identical. So that confirms that either method should be appropriate going forward. The next question that we need to ask is how to handle the completions, and more importantly, the fracture locations. Because we have 10 wells in this model, we're going to end up with different fracture and different cluster and different stage spacing for each of the wells. As a result, we'll have some cases with the top image here where we have a nice even fracture spacing based on our grid block size, and then some of our wells will have an uneven fracture spacing. What's important though is the first bullet point, and that's that we make sure that we honor the second bullet point, that we need to honor the total active fractures for each well. It's okay that we will have maybe some gaps or some fracs that are right next to each other, basically uneven frac spacing, as long as we honor the total number of active fracs for each of the 10 wells. Okay, so the last point that I want to go over in terms of the initial model construction is about the GOR and the bubble point. So we had a single PVT sample for this particular pad. However, this PVT sample was not taken from any of the 10 wells. If we also use that single PVT sample, these wells are undersaturated, so the initial producing GORs would then be the same for them. However, looking at the producing GOR data, we could see that for each of the individual wells, it was actually different. And what we noticed is that the producing GOR actually varied with depth, sort of indicating that maybe we have a compositional gradient. So in IMIX, we can put in a bubble point versus depth table, which basically translates into a GOR versus depth table to represent that changing initial solution GOR. So once the model is constructed, we can lead into our history matching portion. So within the history match, first thing that we noticed is that there were 3 different treatment designs or fracture types belonging to these wells. So we have the slick water frac jobs, cross-link frac jobs, and then slick water cross-link hybrid. So basically a different frac fluid used for each of the different types of treatments performed. The slick water fracs, they were done on wells 1A and 1B. These fractures were determined that these wells the fractures for these wells are contained within the Bakken and don't actually extend lower, and they showed a lower GOR. The crosslink fractures are for wells 1C, 1D, 1E, and 2A, and these fractures can potentially extend into the Three Forks. Because these fractures could go to lower depths, they had a slightly higher GOR compared to the slickwater fractures. Lastly, our third type is the slickwater crosslink hybrid, and this is performed on all of the child wells in development area 2. And also it should be noted that two of the child wells were actually completed in the Three Forks, and they had the highest GOR, so the lowest depth, just indicating that we have that gradient or difference in the GOR. Okay, so let's talk about the history match procedure. So we took kind of a logical step-by-step approach to the history match so that we could sort of match each segment or certain elements of the simulation model at a time and then move on to the next section. So first we'll begin by history matching well 1A. Because this well was performed with slickwater fracs, which are contained within the Bakken, we can use this model or this history match of this well to get the relative permeability as well as the matrix properties for the Bakken reservoir. We can also use it to get the slickwater fracture properties. The next step is to history match well 1E. And when I history match well 1E, I want to take the history match values, particularly for the Bakken, from step 1 and apply it to this well here. So I don't want to make any sort of local modifications since I already have done a history match on the Bakken reservoir for this region. But from well 1E, I should be able to get my Three Forks fracture properties. And because the crosslink fracture extend into the Three Forks, that's why I can get those properties. I also get the crosslink fracture properties here as well. Next step is to then history match the remaining wells in development area 1. And because the remaining wells in development area 1 are composed of either slickwater or crosslink fractures, which have been history matched, ideally I shouldn't have to make any additional changes. Basically, I can apply my history match properties to these wells, and it should match the historical data. Now, if it's not matching, we will need to investigate why, and it may require just maybe some small adjustments to the model. The fourth step is then going to be to history match development area 2 in a single model. The key takeaways from doing this history match are going to be to get the third fracture type fracture properties, which is the slickwater crosslink hybrid. And then also, which is more important, is the history matching the overlapping or the child-parent interactions. So on the screen here, we see the history match results of well 1A of the single well model. The historical data are the darker lines, and the thinner, sort of brighter lines are the simulation model. So this one should be relatively easy to get a good match because we have the most freedom here. We're changing the fracture properties as well as we're changing the matrix properties. Next, we can take a look at well 1E. Well 1E, we're fixing the Bakken properties from the previous history match, and to get a history match here, we're only changing the frac properties and the Three Forks properties. We get a pretty good history match. The only spot where we don't have maybe the best history match is a time when the BHP was not actually measured at that time. Once we've history matched those two wells, we can then apply it to the remaining 3 wells of development area 1. I'm not going to go through every single plot, but just highlight a few here. So here we have well 1B and well 1C. And we did have to make very small adjustments just to make sure that these wells were still matching, which I'll explain at the end of this section. There are a few parts where we weren't able to get a match, but usually that was explainable. For example, in the bottom right, well 1C, a rod pump was installed, but the calculated BHP did not take that into account. And then here are the plots here for well 1D. So let's talk about development area 1 and some of the history match properties or things that were changed in the simulation model to actually get a history match. So first we have permeability in the vertical direction, or permeability K. And really what was important is to make sure that we're correctly modeling the shale layers. If each layer was modeled just sort of regularly, we would end up with way too much pressure support, particularly from the lower layers. So we need to make sure that the shale layers have a very low vertical permeability, so either 0 or close to 0. And only until a frac actually penetrates or goes through the shale layer, then will we be able to establish communication between the different formations. The next point is we used compaction tables for different regions. So a compaction table is basically a function or a table that used to describe the relationship between permeability or conductivity as a function of pressure. And we use this to model the fracture closures. So as we deplete the pressures, the fracture will close, as well as the loss of permeability in the matrix as well. So we included ones for the fracture as well as for the matrix. We used a different relative perm curve for Bakken and Three Forks, so just 2 rel perm curves here, one for Bakken, one for Three Forks. As mentioned earlier, we had to implement a bubble point versus depth table. We did initially try to get a history match just using a constant PVT sample or a constant bubble point, but weren't able to. And then lastly, we have the matrix perm for this particular case, particularly in the shale layers. There was some uncertainty in the measurement of the permeability in the shale layers. So that was key for us getting a history match. So those were the reservoir properties. I'm now going to shift and talk about the hydraulic fracture properties. So again, we're using planar fractures to represent our hydraulic fractures. So for the slickwater fractures, it was determined that they had a larger half length compared to the cross-link fractures, as well as a smaller height compared to the cross-link fractures. The initial water saturation within the fracture was used to match the water production, basically mimicking the frac fluid injected. And it was determined that we had 4 fractures per stage, or 4 active fractures per stage, based on the cluster efficiency. For one of the wells, based on the grid size that we initially chose, the actual number of active fractures became less than our initial grid size. So in order to take that into account, we had to increase the stimulation around that well by including a NFZ perm multiplier, or NFZ stands for near fracture zone. So the near fracture zone is basically the grid blocks just immediately adjacent to the hydraulic fractures. Next, we have the cross-link fractures. For the cross-link fractures, it was determined that we had 2 active fractures per stage. And something here that's important to note is that a couple of the wells, so we history match well 1A, then well 1E, and then when we went to history match, or basically apply the properties to B, C, and D, a couple of the wells were a little bit low on water production. And the reason for that is because we needed to basically lower the fractures very slightly to be closer to the water zone. The initial model that we built was quite coarse in terms of the layers towards the lower depths in the water zone, which is why it wasn't captured initially. So once we lowered the fracs for slightly a few meters, then we were able to get the water production match. Okay, so now let's go into development area 2, and we'll start by talking about well 2A. And with well 2A, it should be relatively easy to get a history match at the start because it has a lot of the same properties as the wells in development area 1. Now, we do get a pretty good match. However, up until the point that we actually have our child wells drilled, and I've highlighted on one of the plots here in the bottom left, that once we have interference from a new well, then we're no longer able to get that history match. So we need to make sure that we're capturing that behavior or interaction correctly. So this slide here, I'm going to explain how we actually are able to get that history match, and I'll show through a video. Before showing the video, I'm just going to explain what our setup is here. So on the left, we have an aerial view of 2 wells. The right well is our parent well, and the well on the left is our child well. So the parent well, you can see it's already got the refinements representing where the fractures are, but the child well is we just have a black line here representing where the well is located. In the bottom right, we have a gun barrel view, or basically where the wells are going into the page. We can see the parent well again is located on the right, and the child well is located on the left. So as I play this through time, we should be able to see the pressure start to deplete solely around our parent well. After the parent well has produced, we then are going to frac our child well. And you should see the child well fractures get created. So in order to get this match, it's not as simple as just applying a child well next to the well. We need to make sure we're taking into account a few things. So the first is to make sure that we have overlapping fractures. So as you can see in the image here, at the gun barrel view, we can see those fractures actually connecting into each other, as well as the image on the left where we can see the fracs basically from the child well grow into the parent well fracs. The next step is to make sure that we have an increased water saturation inside the child well frac, and we can do that recurrently with CMG, and that's going to be to represent the frac fluid of the child well. And then the last point is to make sure that we have uneven half lengths with a preferential growth towards well 1A. If I use even half lengths, my child well fracture half lengths are going to be way too large and I'll struggle to get a history match. So here you can see in the gun barrel view, to the right of the child well frac, we have a much larger half length compared to the left where the half length is shorter. And that's because of that preferential growth into the parent well. So once that's taken into account, let's revisit well 2A and we can look at all the properties and see that we get a much better match at those later times. Not only are we getting an increase in water production from the neighboring well frac fluid, but we're also getting an increase in oil production here. The increase in oil production is coming from basically connecting the child well fracs with the parent well fracs, effectively extending the SRV, or almost the stimulated area of the parent well. We can then history match the remaining wells kind of at the same time. So we have wells 2B and 2C here, which get a pretty good match. And then wells 2D and 2E. 2E is the hardest well to history match since it is the child well that's directly located adjacent to the parent well. So the history match values of development area 2, we didn't make any changes to the matrix properties or reservoir properties and only focused on these overlapping fractures as well as the third frac type, which is the slickwater crosslink hybrid. For these types of fracs, it was determined that the half length is in between the crosslink and slickwater, and the height was also in between the crosslink and slickwater. Again, initial water saturation in the fractures was used to match the water production, and then we used an NFZ per multiplier since frac spacing was smaller than the grid blocks on a few of the wells. And this will be important actually once we transition to the optimization phase, where we want to have cluster spacing as one of our optimization parameters, but we want it to be a continuous function. So we can leverage basically the history matching results. Just depending on the well and the number of fracs that we had, we just had to make very slight adjustments on a per well basis, but nothing major. And then lastly, of course, well 2E was matched with uneven half lengths. Okay, so that's the end of the history map section. I just want to highlight a couple of take-home messages here. So the first point, we actually did just a sort of a qualitative review of the fracture properties, and the half lengths and heights were in line with a third-party fracturing software, just to make sure that we were in the right ballpark. The slickwater, the second point I think is very important. Basically, each frac type, so slickwater, crosslink, or crosslink slickwater, were matched separately, but with common properties. So if one well used a slickwater and we got a history match for that frac type, we then took those slickwater fracs and applied the exact same properties to all of the other wells that use that type of frac. A point that we've said a couple of times, we couldn't match with a constant bubble point, so we had to put in a gradient. Slight height adjustments needed to be made to the wells. We didn't make any sort of local area modifications, so no like local perm mods around any wells, and no major sort of local frac mods, just if it was usually the water production that would be slightly different, and that's just because of the proximity to the water zone. The overlapping fractures were successfully used to match the child-parent interactions, and then we used the NFZ perm enhancements to represent a closer cluster spacing that's smaller than the grid block size. So before transitioning into the optimization, I just wanted to talk about how to model our overlapping fracs. So we need to come up with a way that we can leverage the history match results in order to predict how sort of new wells that we're going to drill are going to interact with parent wells. Now, CMG has geomechanics capabilities, and they work quite well. But in this case, we're looking at doing sort of, a full field case with several wells. And we wanted to take more of a simplistic approach with an analytical model, or sort of an analytical model. We wanted to leverage basically the results from the history match where we calculated those overlapping fracs from the planer and try and use that in our optimization. So the first thing we looked at was the amount of depletion surrounding each of the 6 parent wells. So here I have a plot of pressure as a function of distance. Our parent wells would be located in the center of the plot. And then as we go out towards either the right or the left, the amount of pressure depletion will increase, the pressure will increase closer to reservoir pressure. If we look at a distance that is equal to the original child well fracture distance, so from that development area 2, we can see that the pressure has actually depleted to pretty close or similar values for each of these wells. With that in mind, then on an individual well basis, it won't be so much a function of the amount of depletion, since the amount of depletion is pretty much the same between each of the wells, particularly at this distance and further beyond. So let's take a look at how we'll develop basically our relationship between half length of the child well and the distance it's drilled at relative to the parent well. So here we have a cartoon. On the right is their parent well, which is already drilled, and then we have our child well on the left. I'll apply the child well fracs, and in certain scenarios, we should see those child well fracs grow into the parent, just like we did in the history match. So we know at the distance at which the pressure has depleted to a historical value, we do know the half lengths from the history match. From that, we can sort of represent those half lengths with ratios. So we can say that the half length on the left would be the left side is going to be equal to some factor x times the nominal half length, where the nominal half length is kind of like if this well was drilled with no parent well present. On the right side, the half length will be some factor y times that nominal half length as well. As I move the child well closer and closer towards the parent, we're going to have more and more preferential growth into the parent well and less growth away from the parent well. Eventually, I'll reach a point where the child well maybe has drilled through all of the parent well fracs, sort of a mathematical point, sort of super close to the parent well. At this point, when I frac the parent well, none of the fracs will actually grow away, and all the frac fluid will just go into the parent well fracs, basically just reopening the parent well fracs. As I move further and further away, I'll also eventually reach a point where the left-hand side should equal the right-hand side, which is where my half length will be the same. So we can create a simple function here where I've plotted the half length versus well spacing, where the red would represent our right side or closest to the parent well, and the green would represent our left side or further away. In reality, it's probably not a nice linear function like this, but since we only have the one history match data point, this is the best that we can do. Okay, so we can take that. Now we know how, at least have a better idea of how our child well fractures are going to grow, or at least behave if we drill it close to our parent well. So the first thing in optimization, we have to create a couple of correlations here. And something that as a reservoir engineer that we have to do is sometimes correlate the actual physical or operator input to the simulation input. So on the right, I have a plot of SRV versus pounds of proppant. So basically, this would be relating to our, we're trying to create a function for the simulator. We need half length and height to input, but that should be a function of propant. So we can create a simple correlation, the amount of propant to represent how big the fracts are. On the left, this is going to relate for how we want to look at cluster spacing, or the amount of fracts that we have. We can relate the cluster spacing as a function of our near fracture zone perm multiplier, coming from our history match. Okay, so let's go into the actual model used for the optimization. So the first step is we're going to create a submodel. We could do the optimization on the full model as well, but in this case, we decided to use a submodel first and then go from that submodel to the full model once we've completed. For the optimization parameters that we used, cluster spacing is going to be the parameter, and that's going to translate into the simulator input of NFZ perm multiplier, as well as the actual fracture spacing. Then we're going to have propant, which will translate into half length and height. And we have two well spacings that we want to optimize. We have well spacing 1, which represents the well drilled closest to the parent well. So in the image here, my parent well is in the middle, and then well spacing 1 would be the next adjacent well on either side. And then we have well spacing 2, which would be all successive wells. So that would kind of be in the areas where maybe we have almost like a virgin reservoir or less depleted. And then our final property that we want to look at is how to operate the wells, or basically the drawdown. How quickly or aggressively can we drop the pressure? So for the history mat, or for the optimization, we used CMOST. So CMOST is CMG's history or automated history matching and optimization and sensitivity analysis tool. Basically what it does is it uses artificial intelligence as well as internal algorithms to run many different simulation cases and try and find the optimum combination of parameters that sort of gives the optimum for a particular objective function. So for our case, our objective function was net present value, and we're going to see the results of our CMOST runs in the next few slides. So the first here we have two plots. So the plots here represent NPV as a function of half length in the first plot, and NPV as a function of NFZ perm multiplier in the second plot. We can see that each of these dots would represent one of the cases or combinations of parameters that CMOST ran, so one of the simulations. So we can see that we run quite a few cases, and then the red dot would represent our optimum case. So in the case on the left, the half length was kind of showing in between sort of our minimum and maximum, sort of indicating that maybe basically the range of propant injection that we were looking at in sort of that mid-range, it was the optimum. The next case is our NFZ perm multiplier, which translates into cluster spacing. It's kind of looking at the lower end of the perm multiplier, or that near fracture zone perm multiplier, which correlates to less stimulation. So basically this is indicating that we don't want to sort of include as many fracts as possible, and it does pay to have some sort of cluster spacing to our fracts. The next page is the more interesting results here, where we look at our actual well spacing. So on the left, we have NPV versus well spacing 1, and then NPV versus well spacing 2. We can clearly see a difference in our optimum case, whereas well spacing 1 is promoting a much larger well spacing compared to well spacing 2, indicating that first well that we drill should be at a larger distance compared to all the successive wells, assuming those successive wells are drilled at the same time. What we can see on the image on the left is once we kind of get past a certain distance, the results become less sensitive. So as long as we're kind of at a safe distance for that child well, it shouldn't matter too much. But if we drill it too close, then it could be detrimental. For well spacing 2, we kind of have a nice narrow range where it's kind of optimum. So there's not one exact well spacing, but as long as we're in sort of a range of values, it should be okay. So the points on this slide basically just summarize what I was saying previously. Just quickly go over them. The results showed that we needed a cluster spacing not at the closest spacing. So we don't want to have just basically as many fracs as possible. We have less than the maximum mass of proppant may be ideal for this particular case. In well spacing 1, it was sensitive to spacing when it was very close, but once at a safer distance, the results were less sensitive. In well spacing 2, we could get a small narrow range where values were appropriate. So the final parameter that we wanted to optimize also is the drawdown, or how aggressively to lower the pressure or the bottom hole pressure in these wells. So I've simplified the plots here, and we're just looking at MPV with well spacing 2, and we've fixed all other sort of parameters. From this, we can see that the fourth well spacing that we investigated here was sort of the optimum. Now, if I redo the optimization, or basically rerun these same cases with a more aggressive drawdown, so that would be maybe we have the ability to install a pump and draw down at a lower pressure earlier, we can see that well spacing 3 is actually the most optimum, or the third well spacing investigated. And the reason for that is explained in the next plot, where I compare the cumulative oil as well as the oil rate for the aggressive drawdown case versus the original drawdown. The aggressive drawdown is represented by the solid lines, and the original drawdown is represented by the dashed lines. We can see that overall we're producing the same oil, but it's when we're producing that oil that's different. With the aggressive drawdown, we're able to produce more oil early. And if we think to our net present value, or NPV formula, it will heavily discount basically oil that's produced at later times. So in other words, money made today is worth more money than money made in the future. And so this is why it promotes a little bit closer of a cluster spacing if we are able to operate these wells a little bit more aggressively. So once we've done the optimization on the submodels, we can then take a look at the full model to make sure that our conclusions are still applicable. I'm just going to show two scenarios. Several cases were run through the course of the project on the full model, but I'm just going to show two. The first scenario here, this is sort of our optimal case where we used a larger well spacing. And in this case here is where we had an increased well density, sort of assuming that we had no well interaction effect. So this would kind of be like our ideal case with the hope that each parent well would, or each child well would produce exactly the same as the parent well. So just drilling quite a few wells. So those two cases are compared on this chart here. The orange line represents the sort of the high density well case, and the blue line represents our optimum, which has a fewer number of wells drilled. So as we can see, looking at the first plot, the number of wells obviously is much higher in the orange case compared to the blue case, which directly translates into a difference in capital cost. So basically the capital cost is proportional to the number of wells we have. Looking at the estimated ultimate recovery, we can see that obviously the case with more wells produces more oil, which makes sense. However, we don't see the same difference in terms of cost that we do see in terms of production. So we still able to produce quite a bit of oil from the blue scenario. This leads to our final chart here, which is the NPV, which going from orange to blue, we see a big increase in net present value. And just for those two cases in particular, it was a 75% increase. So let's just go over just a few of the things that we talked about today. So from the model building side, which was our first section, for large models, grids can be oriented in the direction of the wells, but we need to make sure we correctly take into account how the fractures are, or the effective fracture half length. We can use the near fracture zone perm multiplier when frac spacing is less than grid block size. And that helped us actually when we went to the optimization where we wanted to have cluster spacing as a continuous function. Next, we can look for the history matching. To history match multi-well unconventional cases, it's important that we group the wells based on fracture type and that those results make sense. We don't want to history match basically all 10 wells individually and then end up with different properties for each of those wells, as we may end, it'll lose our predictability when we go to the optimization stage. Overlapping planar fractures can be used to history match fracture hits. For optimization and forecasting, using a formula based on pressure depletion, uneven half lengths, and history match could be used to predict a frac hit. And appropriate forecasts can be made without using geomechanics for these large-scale field models. If we're looking at maybe a few wells, then we might start to incorporate some more physics. Interactions from wells will result in a larger than expected well spacing. So even just ignoring maybe parent-child, just the fact that I have two wells drilled at the same time next to each other, the interactions between those wells will promote a larger well spacing. From the NPV calculations, though, it's important to note that it will favor early time production. So any way we can sort of promote getting more production early. So this will promote a closer well spacing if we are using a more aggressive drawdown. But we have to be cautious if the wells become too close, then we refer back to the previous point, and then they start to interact. So at this point, I just want to say thank you very much for your attention. And I'd also just like to thank once again Continental Resources for allowing us to present this webinar. And with that, I'll just pass it back over to Anjani.
Thank you, Kevin. We will now open up the floor for questions. If you have any questions and have not already submitted it in the chat window, you can do it now. I see there are several questions already posted in here. So we will go one by one and take as many as we can, time permitting. Also, due to confidentiality, I will not be repeating the name of the person asking the question. So the first question I'd like to take is, was stress shadowing included in the fracture modeling? Kevin?
Okay, so for the frac modeling, so there was kind of two types of frac modeling. We looked at the sort of a third-party software initially. We did some frac modeling there, and then we used that to just validate our history matching results to ensure that the planar frac history matching that we got was in line with the third-party fracture modeling software. And then for the predictions, we were more basing it on our history match behavior. So how the child wells behave from the historical data to then represent how that will behave for the predictions. So for this particular project, we didn't do any geomechanics, which would incorporate the stress model, the stress shot.
Yeah, and we could have, if the project required, we could have used a full geomechanics-based hydraulic fracture model in the CMD tools itself that would account for the stress shadowing effect as well. We'll go to the next question. Just curious which fracturing fluid was performing the best, slick water, cross-link, or hybrid? Have you integrated any geomechanics? And lastly, when you use NFZ to assign the distance where the perm is changed by fracturing, how do you know if the perm is better or worse than before?
So the first part, I don't know, I don't want to, because this is a client project, I don't want to say which one was better, but we did kind of use that also as a history matching parameter. We're looking at the different frac types. So I don't want to say which one is better just because of the client data. And could you repeat the second part of that question, Anjani?
Yeah, when you assign or use NFZ as a measure of distance, how do you know that by changing the perm, is the perm any better or worse than before? So, I mean, the question is mostly like the NFZ is used to model microfractures that kind of originated from the primary hydraulic fractures. It is either because of opening of the existing sealed fractures or microfractures or creation of microfractures. So the permeability in NFZ is definitely lower than the FZ, which is the primary fractures, but it is slightly higher than the matrix permeability. So in absence of data, predominantly NFZ is more or less used as a history matching parameter as a value which is slightly higher than the matrix permeability.
Yeah, and I'll just add to that. Basically, with the NFZ perm multiplier, it's always a multiplier, so it's always an increase in stimulation. And basically, we're just trying to increase the stimulation if we had a frac or one planar frac per grid block, but maybe our cluster spacing is smaller than that. And with some of these frac types, particularly the slick water, we get more of a complex shape in terms of our frac type. So it's not that perfect planar, which sort of lends itself to the justification of using an NFZ perm multiplier, which is essentially there to represent extra stimulation that can't just be purely captured through a single planar fracture. So the NFZ perm multiplier is there to basically account for the additional stimulation.
Yeah, yeah. The other question is, and I think this question was asked before you presented the post-frac data and history match, is do you use post-frac results for any history match in this study? And I think you already showed that the impact of the frac on the child well and the parent well, and the history was included in the history matching, and the response was very clear and different. So I think that question got self-answered in your presentation later on, unless you have to add something in addition.
No, just in case they're referring also to the third-party fracturing. Again, we used those just to make sure that are the fracture properties we're getting for slick water and crosslink making sense with what those sort of were predicting.
Yeah.
They were.
The other question is, does aggressive drawdown have any geomechanical impact on the matrix in the Bakken?
So that's a good question. So we did include the compaction tables as part of the simulation, which will represent basically the fracture closure. So as we rapidly decline that pressure more aggressively, we should see the fractures actually close quicker, and we would expect to see some sort of resistance to flow. Now we're just in this particular project, we're just doing it based on the history match. Some of the wells were operated with a more aggressive drawdown, and some were operated with a less aggressive drawdown, so we did have the data available. But if we maybe didn't have the data available, we could easily add geomechanics to some of these models and just see how the stress is changing when we operate with a more aggressive drawdown.
Okay. The next question is, can you share your thoughts on relative permeability of water in the Middle Bakken and Three Forks? Some data analysis suggests water relative permeability is near zero for Middle Bakken. How would pressure be impacted with radical relative permeability curves?
Yeah, I mean, like for this particular case, we didn't have any relative permeability data initially. So the starting point was just a literature review. From that, you have to look at the data itself. So for example, if we look at the water production in an unconventional reservoir, if you see the water production fall off very quickly, where you don't see any, it's basically could mostly be accounted for as frac fluid production. However, if you see wells where the water production is sustained for long periods of time, then that usually indicates that we have some sort of source of water production. In this case, that could be either mobile water or a high water saturation zone. If we have a mobile water zone, which is a lot of the times the case in some of these unconventional reservoirs, when we have mobile water, basically then we have capillary pressure that holds that mobile water in place until we start to deplete the pressure.
Yeah, and what we have seen is like when you produce the well after fracturing, the water cut is quite high, and then it drops, gradually drops to a certain value, and then stabilizes for a very long time. So the initial portion is definitely from the frac fluid, but as Kevin said, is a lot of the water is retained in the hydraulic fractures because of capillary pressures and other things. And if the water is getting produced and is stable for a long period of time, I'm talking about like a year or 2 years, then there is some mobile source of water. And you can also do some volume variance calculation, is how much water has been pumped into the reservoir as a result of hydraulic fracturing and how much you are producing. So if you are producing, because normally there's almost 40 to 50 or 60% of the frac fluid water should be retained in the hydraulic fractures in the bottommost parts of the fractures. But if you're producing significantly higher numbers in terms of volume, then definitely there's some additional source of water. The next question, and probably we'll be taking a few more questions, and then because there's a lot of questions here I can see, and time permitting, we may not be able to take all of these questions, but we will definitely get back to you, to each one of you, with the answers to your questions. So the next question is, was the optimization done on each variable separately with all other variables fixed? How does CMOS take into the combination of variables into account?
So the optimization was done with all variables together. So we would include half length, cluster spacing, and the well spacing all together. So that was kind of the first part of the optimization. We did do a couple of optimizations. We did kind of several just to see how it would play out, where we would fix the properties, particularly because well spacing was so important for this study. We might just fix all the properties and just look at well spacing. That was done as well, just to kind of validate the results from the other studies that were done. But with CMOS, the luxury of CMOS is you can include as many parameters that you have and want to include. And so that's why I just go back to those images. We end up with these images with all these different dots, and these different dots are representing basically a different combination of my input parameters. So initially how CMOS would work, it'll depend on the optimization algorithm that we've chosen, but basically we'll start with an exploration stage. In an exploration stage, we're kind of trying to choose different combinations of parameters to make sure we're kind of exploring the search space. So we might choose, say, a large value for well spacing 2, but then a small value for well spacing 1. And then conversely, we might run a job with well spacing 1 as high and then well spacing 2 as low. So we run them depending on the number of parameters. Let's say we run 20 or 30 jobs. Once CMOS has run those jobs, it'll look at the data and sort of start to develop a trend. And it'll see sort of, depending on our optimization algorithm, it'll start to sort of narrow down the search space. So if we use the CMG DECE optimization algorithm, then what it's doing is it'll kind of look at each variable, kind of see where that variable is sort of optimum. So you'll see we have more cases run near our optimum because CMOS has sort of learned that, okay, large values of well spacing 2 or really small values are not producing optimum results. So I'll start to narrow my search space. And so as it kind of runs successive sort of iterations, it'll slowly narrow that search space. Another example would be sort of like a proxy or the proxy optimization, which builds a proxy that fits the data, the input values to our objective function. And then with the proxy formula, it'll use that proxy formula to find what the optimum combination would be. And then it'll run that simulation, validate it against the proxy, and then update for a new proxy and run it. So those are just a couple examples. Hopefully that was clear.
Okay, we can take one more question here. Can you help us understand the implication of SRB pore pressure that is at or near the saturation pressure for the producing zone? In other words, if the pore pressure approaches or drops below the saturation pressure, would you expect the child to adversely affect the performance of the parent well? The question is about a condensate reservoir where you drop below the dew point pressure and the liquid starts to drop out, and how does that affect the child well's performance or the parent well's performance?
Yeah, in this particular case, we had use a black oil that was undersaturated. So when we dropped below the saturation pressure in this case and gas came out, we didn't see too much of a negative impact. That's kind of why we could operate with a more aggressive drawdown. If we are near the saturation pressure initially, so if we are saturated reservoir, or like Anjani said, if we have a condensate reservoir, if we operate those wells too aggressively, then we should see sort of the liquid, or in the case of a black oil or volatile oil, the gas dropping out quicker when we drop the pressure quickly, and then that can adversely affect sort of our production of the liquid. So in terms of the child well performance, it will for sure affect it because it's being drilled into a depleted zone. And if that zone is depleted past the point of bubble point, then the rel perms will of course promote the flow of gas relative to oil. So it will for sure affect it in the case of parent-child interactions when we have heavy depletion.
All right, thank you, Kevin. And I mean, I see there's a lot of questions in here, which unfortunately we cannot take it live, but we will definitely follow up with each one of you and answer and provide an answer and solution to your questions. But again, I'd like to thank everybody for attending and tuning into the webinar today. I'm sure that the workflows shown today will be useful in optimization of the well density and minimizing negative impact because of parent-child interactions. If you want to learn more about unconventional modeling approaches in CMG, there we offer a multitude of training courses. But in the current environment, we have moved most of our training courses online. So do watch out for training courses that are being posted on our website, on LinkedIn, on social media platforms. We do have recorded versions of those training materials available in the resources section of our website. So do check it out. There are a lot of how-to videos on our YouTube channel. So those are really helpful tools to get yourself familiar with the different workflows. We will also post the recorded version of today's webinar on our website within the next 24 hours. So log into cmgl.ca and use your CMG username and password to access that material. So again, thank you for joining us in today's webinar. We appreciate your interest in CMG and in these economic and other hard times. Our best wishes with you. Stay safe and stay healthy. Till next time, thank you very much.
Thanks, everyone.